Section: Introduction. In this section, we discuss the rise of large-scale machine learning models like Gemini, GPT-4, and Claude, which have become popular due to their ability to handle various tasks. These tasks include understanding and generating natural language, such as translating languages, summarizing text, and creating conversational agents, as well as computer vision tasks like recognizing images and detecting objects. The flexibility and effectiveness of these models make them essential in fields like healthcare, finance, education, and entertainment. However, using these large models comes with challenges related to speed, memory, computing power, and storage. Optimizing the costs of using these models is an active area of research. This includes methods to reduce the size of existing models, such as compressing, pruning, and distilling them, as well as techniques that use a sequence of models, like speculative decoding and model cascades. Given that larger models generally perform better, the latter methods are currently seen as more promising for reducing costs without losing performance. Both speculative decoding and model cascades depend on having a large, high-performing model and a smaller, faster, but less accurate model. In speculative decoding, the smaller model generates draft tokens that the larger model then checks in parallel. In contrast, model cascades use a strategy to choose the best model for each request. While speculative decoding requires a capable smaller model to produce quality drafts, model cascades can work with a less capable smaller model by only using the larger model for requests that the smaller one cannot handle. Our work focuses on improving model cascades, which balance two goals: computing budget and overall accuracy. We illustrate this balance with an example involving inference requests and a smaller model that uses only a fraction of the resources of the larger model. We identify 4 scenarios regarding how the smaller model handles requests, ranging from deferring all requests to the larger model to only sending those it would get wrong. We aim to optimize model cascades to enhance what we call deferral performance, which is how well the smaller model can identify when to defer to the larger model. To achieve this, we introduce a loss function named Gatekeeper, which helps the smaller model better understand its confidence in its predictions. By training the smaller model to be confident in correct predictions and uncertain in incorrect ones, we improve its reliability and learning for common tasks, thus enhancing deferral performance. Importantly, Gatekeeper includes a built-in way to balance model performance with deferral performance, making it applicable to various architectures, including vision language models. We demonstrate the effectiveness of the Gatekeeper loss across different model types, showing that models trained with it significantly outperform untuned models in terms of deferral performance. This progress opens up new possibilities for deploying models more efficiently, combining the strengths of both small and large models to achieve high-quality results in real-time applications. Section Summary. In this section, we discuss the growing importance of large-scale machine learning models and the challenges of deploying them efficiently. We introduce our approach, the Gatekeeper loss function, which enhances the small model's confidence in its predictions to optimize model cascades for better deferral performance, ultimately improving the balance between accuracy and compute budget across various architectures. Section: Related work. In this section, we discuss related work that informs our proposed method, which enhances model cascades through uncertainty-aware fine-tuning. Model cascades involve a series of models and a rule that decides which model to use based on the input. This concept was first introduced to speed up object detection models and has been widely explored in classification tasks in computer vision and natural language processing. Cascades are particularly beneficial for generative models like large language models, LLMs, and vision language models, VLMs, because they can lower inference costs by only using the larger model for more complex cases. While speculative decoding and model cascades can be combined, most research has focused on using pre-trained LLMs with a post-hoc deferral logic. Some studies have used agreement among multiple models to make deferral choices, while others have developed methods to learn deferral rules based on the distribution of log probabilities. We can enhance model cascades through training and fine-tuning, such as training smaller models on easier examples and adjusting the training objectives for image classification with confidence calibration. Our work extends these cascades to VLMs, improving inference performance by reducing the confidence of smaller models when they make mistakes. In the area of uncertainty-aware models, significant research has been conducted on quantifying uncertainty in deep learning. While many techniques exist for classification models, measuring uncertainty in generative models remains an ongoing challenge. We categorize existing methods into three types based on access to model internals. 1. Black box methods, which modify prompts to encourage less confident responses. 2. Gray box approaches, which focus on post-processing model outputs. 3. White box methods, which use fine-tuning to create better calibrated models. Our method aims to ensure that correct predictions have low uncertainty and incorrect ones have high uncertainty. We consider this uncertainty-aware model within a cascade inference system to enhance overall performance. Previous work has suggested pre-partitioning data into easy and hard sets for training, but we improve this by dynamically assigning examples based on the current state of the smaller model during training. Our framework consists of a large, capable model and a smaller, efficient model. We assume the smaller model has fewer parameters than the larger one. Both models can serve as classifiers or sequence models, and we conduct experiments across these types. Importantly, the two models do not need to belong to the same family. For instance, the smaller model could be a custom neural network while the larger one is a vision transformer. The main goal is to create a deferral mechanism that allows the smaller model to decide when to make predictions independently and when to defer to the larger model. We derive deferral signals from the smaller model, as this is generally more cost-effective than using a separate routing mechanism. We avoid methods that require querying the larger model for deferral decisions, as this undermines the purpose of our approach. We assume that the smaller model is less capable than the larger one, which is a common scenario. Mistakes made by the larger model are also likely to be made by the smaller model, but the smaller model may make additional errors. We have full access to the smaller model's internals, allowing us to integrate deferral mechanisms directly into its architecture. Our work proposes a new loss function for fine-tuning the smaller model, aiming to train it to effectively distinguish between correct and incorrect predictions. We focus on whether we can optimize the smaller model to separate these predictions, and we demonstrate that this is achievable through a well-designed fine-tuning process that does not require changes to the model structure. Section Summary. In this section, we review related work on model cascades and uncertainty-aware models, highlighting how cascades can enhance performance in generative models by reducing inference costs and how uncertainty quantification methods can improve model calibration. We also discuss our approach to dynamically training a smaller model to effectively distinguish between correct and incorrect predictions without requiring architectural changes. Section: Confidence Tuning for Deferral. In this section, we outline our approach to confidence tuning for deferral. Stage 1 involves standard training, where we start with a model, referred to as M_S, that has already been trained for its intended tasks. However, M_S has limited capacity and cannot perform as well as a larger model, M_L. We do not make any assumptions about how M_S was trained, whether from scratch or through a distillation method. In Stage 2, we implement a correctness-aware fine-tuning process using a loss function we call Gatekeeper. This function helps M_S improve its confidence calibration by training it to make accurate predictions with high confidence while lowering the confidence for incorrect predictions. We can use either true labels or the outputs from M_L as targets. The calibration loss combines several elements, including true and predicted labels, predicted probabilities, and a uniform distribution over classes. A key hyperparameter, alpha, controls the balance between focusing on correct and incorrect predictions. A lower alpha value encourages the model to be cautious with incorrect predictions, while a higher value boosts confidence in correct ones. By adjusting alpha, we can tailor the model's behavior to achieve a balance between reliability in uncertain areas and decisiveness in confident predictions. We also extend this loss to token-based models, ensuring that correct token predictions are made confidently while incorrect ones receive lower confidence scores. In Stage 3, after fine-tuning M_S with Gatekeeper, we apply standard techniques to compute confidence and uncertainty, which helps us decide whether to accept a query point or defer it to M_L. We introduce a gating mechanism that determines if M_S should make a prediction or pass the query to M_L. This mechanism uses a deferral function that assesses whether to accept or defer based on a set threshold. For classification models, we define the gating function based on the categorical distribution produced by M_S. For token-based models, we define it using the sequence of categorical distributions for each token. Higher values from these gating functions indicate greater confidence in the predictions. Section Summary. In this section, we outline a three-stage process for enhancing the performance of a smaller model, M_S, through confidence tuning. We first fine-tune M_S using a correctness-aware loss called Gatekeeper to improve confidence calibration, then implement a selective prediction framework to determine when to defer to a larger model, M_L, based on confidence thresholds. Section: Experiments. In this section, we describe the experiments we conducted to evaluate our deferral strategies using three different model types: encoder-only classification models, decoder-only language models, and encoder-decoder vision language models. Each setup tests how well we can defer challenging queries to more capable models, moving from smaller to larger models. For the encoder-only setup, we start with image classification. We train both a large and a small model on datasets like CIFAR-10 Food 101, and Tiny ImageNet 200. For the CIFAR datasets, we use a RESNET18 as the large model and a custom CNN as the small model. For Food 101 and Tiny ImageNet 200, we switch to a RESNET50 for the large model and a MobileNet v3 small for the small model, which is trained using knowledge distillation from the larger model. To evaluate our methods, we look at several performance metrics. One key metric is the distributional overlap of confidences, which measures how well the small model can distinguish between correct and incorrect predictions based on their confidence scores. If the overlap is 1, the small model cannot tell the difference. If it's 0, it can perfectly separate them. We also consider the area under the receiver operating characteristic curve as another way to assess this separability. Next, we quantify how effectively the small model defers difficult inputs to the large model. We analyze performance across different deferral ratios, which represent the fraction of inputs sent to the large model based on a specific threshold. As we increase this ratio, we observe that the overall accuracy improves from the small model's accuracy to that of the large model. Effective deferral models should perform better than random deferral but not exceed the ideal deferral, which perfectly defers misclassified examples. We also define the realized deferral curve, which reflects the accuracy achieved under our learned deferral strategy. The deferral performance metric indicates how much improvement we gain over random deferral. A perfect score means we match the ideal strategy, while a score of 0 means no improvement. Finally, we note that while our Gatekeeper method helps distinguish between correct and incorrect examples, it can lead to a decrease in the small model's overall accuracy. Therefore, effective deferral strategies must balance deferral performance with the small model's accuracy. In our results, we present performance data for both a baseline model and small models trained with Gatekeeper at various settings. We find that lower settings yield better deferral performance but at the cost of the small model's accuracy. Conversely, higher settings maintain or even improve accuracy but may not enhance deferral performance as much. This illustrates a trade-off between overall model utility and deferral effectiveness, a balance that is also seen in areas like fairness and privacy. We explicitly analyze this trade-off, showing a negative correlation between deferral performance and the small model's accuracy, and a positive correlation between the overlap of correct and incorrect confidences and the small model's accuracy. Section Summary. In this section, we evaluate our deferral strategies across 3 model architectures by training both large and small models on various image classification datasets, measuring performance through metrics like distributional overlap of confidence scores and deferral performance. Our results reveal a trade-off between deferral performance and the accuracy of the small model, indicating that optimizing for better deferral can lead to a decline in overall classification accuracy. Section: Decoder-only setup, language models. In this section, we explore the decoder-only setup for applying large language models, LLMs. Our focus is on the scalable models from the Gemma class, specifically Gemma 2B with 2 billion parameters and Gemma 7B with 7 billion parameters. Similar to the encoder-only setup, we use smaller models as initial classifiers for simpler next token prediction tasks. We implement a deferral strategy that directs only those token sequences with high uncertainty, indicated by high predictive entropy, to the more powerful model, Gemma 7B. We begin our experiments by fine-tuning both models on the training split of their respective datasets to ensure they perform well and are familiar with the desired response format. This fine-tuning uses standard perplexity minimization. Next, we fine-tune Gemma 2B with Gatekeeper to reduce confidence in incorrect predictions before evaluating the model on a validation test split. The datasets we analyze include ARC-E, C, MMLU, and GSM-8K, and we use the same evaluation metrics as before. We present our main results in a figure, comparing the baseline model's deferral and separation abilities against our fine-tuned model at various thresholds. We generally observe that higher thresholds maintain prediction performance similar to the baseline but do not significantly enhance the separation of correct and incorrect predictions. Conversely, lower thresholds improve deferral significantly but reduce overall accuracy. In addition to the baseline model, we also evaluate 2 other uncertainty prompting methods, one that encourages the model to reduce confidence when uncertain, and another that instructs the model to respond with N if unsure. However, we find that these methods do not reliably improve the separation of correct and incorrect predictions or serve as effective deferral models. Next, we examine the encoder-decoder setup with vision language models, which are suitable for tasks requiring both visual and textual understanding. We focus on the Poly-Gemma model family, which is designed for tasks like image captioning and visual question answering. In this setup, the encoder processes images to extract features, while the decoder generates text. We use Poly-Gemma 1B as our smaller model and Poly-Gemma 7B as the larger one. The deferral strategy here involves using the smaller model for most tasks and reserving the larger model for cases where the smaller model's predictive entropy is below a certain threshold. We again perform 2 stages of fine-tuning on both models before evaluating them on a validation test split. The datasets include 2 classification datasets and 2 captioning datasets, allowing us to assess Gatekeeper in both classification and text generation contexts. For the captioning tasks, we compute a factuality score to evaluate the quality of generated captions. This score assesses whether the generated caption is semantically coherent with a reference caption using the Gemini LLM. We prompt the model to determine if the captions are equivalent and then calculate the log likelihood of its response, normalizing it to reflect confidence in factual alignment. To measure the correlation between factuality and negative predictive entropy, we replace our previous accuracy-based metrics with the Pearson correlation between the negative predictive entropy of a caption and its factuality score. We adapt our deferral performance metric to rely on factuality measures instead of accuracy. We document our results, showing that for classification tasks, we observe similar trends as in our earlier experiments. For captioning tasks, we find that Gatekeeper significantly increases the correlation between factuality and negative predictive entropy, leading to better deferral from the smaller model to the larger one as the threshold decreases. This indicates that our method is effective not only for classification problems but also for sequence generation tasks. However, we note that the Poly-Gemma model did not respond to the prompting baselines from earlier experiments, likely due to its rigid pre-training.